Today's lesson is on ozone depletion. And I want to share with you this tremendous picture that NASA and Goddard Space Center put together. And this was using 3D satellite imagery, and it shows that area over Antarctic that doesn't have any ozone. And because of the Antarctic vortex that's there, it's able to create that crater where the hole is. And every spring, which is around October, it comes to light. And this is a tremendous picture, one of the later pictures they have. And today I'd like to talk about how that happens. Should we be concerned with it, and what are the processes that take place over not only Antarctic but within our atmosphere? So let's go ahead and get started. The first thing I'd like to talk about is just look at our atmosphere and understand what ozone is. Ozone primarily is a triatomic molecule. It's a very, very strong oxidizing an oxidizing agent, and it's really unstable in really high concentrations. It's a pale blue gas, and for the most part, if you've ever been around like lightning strikes, you have that kind of that chlorine smell near it. I'd rather not be around lightning strikes, but from time to time I have been, and it has that kind of strong chlorine smell. That's ozone. And the other thing about it is that typically in lower areas, like in the troposphere, in that area, if there's ozone, that's a bad thing. It tends to be really corrosive, especially to organic materials, whether it be your mucous membranes or plants. It's extremely corrosive kind of material. However, as we go into the stratosphere, it's much more beneficial. So the stratosphere is this portion of it. It goes from about 15 miles all the way up to about 50 miles. That would be the stratosphere. And anything below 15 is what we call the troposphere. This is the area that we live in. When ozone appears in the troposphere, that's what we call bad ozone. It's ozone in here is considered an air pollutant. And I said before, it does to be quite caustic and causes some problems with watering eyes, sore throat, and other respiratory ailments, as well as plant destruction as well. Then we get to the good ozone. The good ozone you'll find primarily right around 30 miles above our head. That particular ozone acts as a shield, so that when UV radiation hits it, it bounces it back up. So it reflects it back out into the outside of our atmosphere, keeps it away from us. It's kind of like sunscreen. I got some sunscreen right here. And so ozone in our stratosphere kind of acts like this stuff for us. And just like we need sunscreen when we go out in the summertime and in direct sun, our planet also needs a little sunscreen, and that would be considered ozone. So think of ozone as that sunscreen we put on. So we have good ozone, we have bad ozone, kind of depending on what part of the atmosphere it's on. For the most part, it's good for the planet to have a good, healthy layer of ozone to reflect back some of the sunlight. If we don't have that sunshine or that sunscreen, UV light gets in, either ultraviolet A or ultraviolet B. So from a biological point of view and an ecological point of view, the sunscreen or the ozone that's in our atmosphere is very much needed. As it's beginning to thin, and as we see less and less of it, we're seeing more and more problems with cancers, in particular skin cancers. In the last few years, there's been 10% higher incidences of skin cancer than, let's say, 30 years ago. Typically, we're going to see squamous cell carcinomas or basal cell carcinomas or melanomas. Those are the most serious ones because they're impacting the pigments that help protect our skin from ultraviolet rays from the sun. So the squamous cells are usually the ones just below our dead skin, and then a little bit further deeper in is the basal cells. So it's really definitely having an impact. But also from an ecological point of view, ozone depletion also means that, for instance, in this particular case, we began to see ozone levels drop dramatically since 1976. We're seeing a small increase in the amount of ozone. It probably reached its peak in terms of depletion around the 1996, in October 1996, when that was the biggest hole. It was like 11.6 or 11.8 million square miles of ozone that wasn't there. That big hole in the ozone was over Antarctica in 1996. That was the largest hole we've seen on record. So ozone depletion is a serious issue that we are watching, and it typically is highest in October and November. Now, what causes ozone depletion? Well, it's chlorofluorocarbons, or CFCs. Another one is ozone depleting chemicals, ODCs. But CFCs, or organic molecules, would have chlorine, fluorine, and also hydrogen atoms. And it was developed in 1930. It's a man-made material. It's developed in 1930 by GM chemists, and they had thought they had really invented the panacea of chemicals. They thought they kind of hit the gold mine because they got something made inexpensively that was non-corrosive. It was non-reactive, and it was colorless and odorless. And like I said before, it was fairly inexpensive, and it can be used for a variety of things. You can kind of compress it so that you can use it as a refrigerant in refrigerators and air conditioners, in particular automotive air conditioners. You can use it in plastics. It's also a great cleaner for all kinds of electronic parts, in particular processors. And it was, well, in an aerosol cleanser, it was a propellant. It was the thing that allowed the aerosol to be propelled into the atmosphere for air freshener or whatever it might be. So, of course, in the 70s and 80s, you saw kind of a change in that. And so CFCs, it was a huge industry, and they had some problems they had to deal with in the 70s, 80s, and 90s, and we'll get to that a little bit later. Now, how does it work? Well, there are two scientists from the University of Irvine, and they were able to work out how CFCs actually harm our atmosphere and how it actually breaks down the ozone. In the presence of ultraviolet radiation, this particular molecule right here is a CFC. So you can see there are 3 chlorines, a carbon, and of course a fluorine. So the CFC, or chlorofluorocarbons, is pretty large molecule. And then how it works is the chlorofluorocarbon will break apart. As it breaks apart in the presence of UV radiation, a chlorine will shake loose, and as it does that, it's going to come in contact with ozone. Ozone, as you can see, is a triatomic compound of oxygens, and then what it'll do is react with chlorine, and it will kind of lop off or tear off an oxygen. And when it does that, we basically have chlorine monoxide. So the chlorine monoxide molecule, or ClO, will also start looking for coming in contact with O2s, and as it comes in contact with O2s, there's always a spare oxygen floating around, so it's going to react, that lonely oxygen that's with the chlorine, it's going to be attracted to that other oxygen to form O2, which frees the chlorine to start the process all over again, so it's able to attack ozone again. So basically what we had here is these two gentlemen, Sherwood Rowland and and Mr. or Dr. Molina, Molina from the University of California, Irvine. And in 1973, they began to research the effect of CFCs on atmosphere. And these are the four things they learned about it. And shortly thereafter, in 1974, they called for an absolute 100% ban of CFCs worldwide because they saw the ultimate destruction it could have. And of course, it went right in the face of DuPont and other manufacturers of CFCs, and it took them 14 years in court battles and other venues before they could actually bring a halt to that. And eventually they got DuPont to admit, yeah, we know it destroys ozone. But up until that point, they called their work fraudulent, and it was a pretty significant battle that they had to wage against some pretty heavy hitters who had lots of resources. But anyway, their research was solid, and it was backed by other scientists doing similar work. So the first thing that they found was CFCs are insoluble in water, which essentially said if it's insoluble in water, then it's going to be able to remain in the troposphere. In other words, it's going to be remaining in the areas that we would inhabit. And so it didn't break down all that well. So and because of the fact that it was able to kind of recycle itself, it stayed because it was unreactive and insoluble. Second thing is the CFCs began to could kind of catch a ride with air currents, with some of the convection currents, and of course the vortex in the Antarctica. It was able to rise to the stratosphere. And why would that be a problem? Well, because there's lots of ozone in the stratosphere it can react with. And as it does that, it can sustain itself in the stratosphere for a long time. Third thing is that CFCs break down ozone with ultraviolet rays. It needs the ultraviolet rays, and so when it gets in the stratosphere, it has everything it needs. It's got the ozone, it's got ultraviolet rays, it's got the winds that will carry it. And the fourth thing they found out is CFCs can last up to 380 years. Because of this being able to be taken to the stratosphere and have this ozone, and they can basically recycle itself, break down some ozone and grab onto another one, it was able to last about 380 years depending on the type of CFC or the ODC that's available. So Roman and Molina eventually in 1995, I believe, or 96, they won the Nobel Peace Prize for working out all of the parts to CFCs and ozone depletion. And here's another picture I included about Antarctic and that big hole over it. And again, that's during the spring months, and you can see that tends to accumulate there primarily because, and this is kind of an interesting thing I think about CFCs, is as they ride the winds and get caught up in the vortex in Antarctic, because in Antarctica, when the winds blow, especially in the winters, they pick up obviously a lot of the cold air and a lot of the icicles, and then as they kind of spin their way up, they're catching all these CFCs, and because it's so cold, it basically freezes all these CFCs, and basically what it's doing is it's keeping it in storage. It freezes it and prevents it from mixing with the ozone, but really what it's doing is concentrating it, and on top of that, it's storing it. So when it gets down to October, November, and the warmer weather starts to melt those icicles, all of a sudden, boom, it starts getting reactive again. It starts taking down some of the ozone. And that's when we see the biggest holes in our planet. About 50% of all of the ozone depletion is going to happen over Antarctica, and it's going to happen during that time when all the CFCs are kind of released from their ice jails, if you will. And like I said before, during the 4 months of each year, half of the ozone in the stratosphere that's over Antarctic and a little bit in the Arctic is depleted because of this thawing out of the ice crystals that have a lot of the CFCs. Now, what happened to all of this? What became of all the research? Well, first thing is in 1987, the Montreal Protocol was established, where it basically went from country to country and city to city, larger cities, signing agreements they would stop or ban the production and use of CFCs. And it was completely phased out by 2000. That chemical was completely... Now, there are a few countries that still produce and are still trying to get their hands on it. But for the most part, the world came to an agreement to stop ozone depletion by not using or stop manufacturing this product. And so by 1996, ozone-destroying chemicals were eliminated by 96, and of course ozone-destroying chemicals also were included in that list in 2000. So in 2000, 1996, we began to see a reduction in the amount of CFCs in our atmosphere. And then the other thing is, and they can verify the impact of the Clean Air Act of 1990 by looking to a lot of the ice cores and where things started to change as far as air quality. So these kinds of proposals do work. So the legislation of the Clean Air Act, it restricts the production and use and emissions of ODCs, as well as regulating the servicing of air conditioners and refrigerants. So basically what this shows us is that we can come together as a planet to be able to protect our stratosphere and clean up our planet. Well, I hope this has helped. This is the last part of Chapter 20 of climate change. We'll be taking a test very, very soon. So I hope that you will look at the website, also take a look at any of the videos and review those. And we'll see you back in the lab in about a week. Thanks.